Alright, it's time to get started, and thank you for coming, if we can say it that way. And so I am going to be honest, and it's been a long time since the last stream, and I don't know what was the state of the PPU registers the last time we was working on it. So in the tutorial itself, I came to this step. The communication with the rest of the register is similar and is left to the exercise of the reader, so it is up to us to decide when to go on. So let's take a look to the PPU registers and see what is implemented and what is not. So we have the control register, the mask and the state register, and we have classes for control, mask and status, and apparently they all are implemented. So yes, we have name table, we have the VRAM add increment, display pattern table, etc, etc. We have the mask register for visual effects and stuff, and showing and hiding background and sprites. We have an update that simply sets the value. And we have the status registers that we only have 3 bytes that we care of. And we don't have an update function, but it's really easy to just copy and paste. And if we ever want to set the entire value in one sitting, we can do it like this instead of changing one flag at a time. So yes, so we have all the bit flags registers in place. The OAM address was working, address and data, if I remember correctly. And you can write to the address, you can read the address, and you can read the data from the address. You can increment the OAM address. So write data is going to get the address incremented and save the value in the right place depending on the range of the memory. Read data is going to get the address and increment the VRAM and get the value from the data depending on the range. Copy RAM to OAM is going to make a replacement of one entire it is not a kilobyte, it is 255 or 256 values, making a ring. Incrementing the OAM address is just a loop around. It always adds 1, and if it goes beyond FF, it is equal to 0 again. VRAM address, it takes the increment from depending on the register flags, and the mirroring of the VRAM address takes care of mirroring the screen, so you get the real address depending on the repeated flags. So I think everything is in place. When we run it, we are still getting the same little errors that are because of the LAU functionalities, as far as I know. So there is a couple of instructions that are not registered at all in the log file, but we don't care of that for now. Yep. So, what comes next? I think we're ready to go to the next chapter, which is emulating the NMI interrupt. Interrupts are mechanisms for the CPU to break the sequential execution flow and react to events that require immediate attention. Attend to an interrupt. We have already implemented one of the supported interrupts, the reset signal. This interrupt notifies the CPU that a new cartridge was inserted and the CPU needs to execute the reset subroutine. CPU communicates that it is entering the blank phase for the frame via another interrupt signal, NMI, non-maskable interrupt. From a high-level perspective, this means two things. CPU is done rendering the current frame, and CPU can safely access the PPU memory to update the state for the next frame. The reason why blank phase is unique is that while the PPU is rendering visible scan lines, it is constantly using internal buffers and memory. External access to input-output registers can corrupt data in those buffers and cause noticeable graphic glitches. Unlike other interrupts, CPU cannot ignore the NMI. The disable interrupt flag in the status register P has no effect on how the CPU attends to it. The CPU, however, might instruct PPU to not trigger NMI by registering the 7th bit of the PPU control register, which is... wait a second, no. This is not the control register. Okay, 7. If you generate an NMI at the start of the vertical blanking interval, so 0 is off and 1 is on, so if you can turn off the interrupts using this byte. Okay, so by resetting it means by clearing the 7th bit. Okay. Clock cycles. The NMI interrupt is tightly connected to the PPU clock cycles. The PPU renders 262 scanlines per frame. Each scanline lasts for 341 PPU clock cycles. Upon entering scanline 241, PPU triggers NMI interrupt. PPU clock cycles are 3 times faster than CPU clock cycles. Nothing beats NES Dev Wiki on providing details on line-by-line timing. But to simplify, each PPU frame takes 2 times 262 equals 89,342 PPU clock cycles. Okay. CPU is warranted to receive NMI every interrupt about 29,780 CPU cycles. So let's take a look to the timing according to NES Dev. I expected some graphic, yes. So visible frame, post-render line, pre-render line. Skip it on background odd. Background is bit address only. So sadly I don't know how to reach this. Okay. So flag operations or miscellaneous blanking. Blanking, I suppose it means it can change the value of the VRAM of the CPU. Vupdate means it is changing the value internally. But I don't know what are the columns. It is timing. I suppose they are cycles. So is this CPU cycle and this one CPU cycle? Okay, no. So this is 1, 2, 3, 4, 9 and this is 10, 11, 12, 13, 14, 65, 64, 249, 250. Okay, I don't really know how to read this, but I hope to not need it used yet. If we ever need information about the timing, we can look at this. But I think we can go with signals for Godot. Note, PPU cycles and CPU cycles are not the same things. Yes, I got that. On the NES platform, all components were running independently in parallel. This makes NES a distributed system. The coordination has to be carefully designed by game developers based on timing specs of the instructions. I can only imagine how tedious this manual process is. The emulator can take multiple approaches to simulate this behavior. 1. Allocate a thread per component and simulate proper timing for each instruction. Don't know of any emulator that does that. Simulating proper timing is a hell of a task. Second, this approach requires allocating more hardware resources than needed for the job. CPU, CPU, and APU would require 3 threads, and potentially would occupy 3 cores on the host machine. Execute all components sequentially in one thread by advancing one clock cycle at a time in each component. This is similar to creating a green thread runtime and using the dedicated OS thread to run this runtime. It will require substantial investment in creating green threads runtime. 3. Execute all components sequentially in one thread, but by letting CPU to execute one full instruction, compute the clock cycles budget for other components, and let them run within the budget. The technically scaled catch-up. For example, CPU takes 2 cycles to execute LDA literal 1 opcode A9, which means that PPU can run for 6 PPU cycles now. PPU clock is ticking 3 times faster than the CPU clock. I wonder, is this an exact value? It is exactly 3 times? And APU can run for 1 cycle. APU clock is 2 times slower. What? What is 2 times slower? Oh, right. So 2 cycles, 1 cycle. Because we already have CPU loop mostly spec'd out, the third approach is the easiest to implement. Granted, it would be at least the least accurate one, but it is good enough to have something playable as soon as possible. So the flow would look like this. we have a loop. It is going to execute an instruction, notify about ticks the instruction took to the boss, and the boss is going to notify about the time ticket to the PPU. PPU is going to execute logic, return control flow, and return the control flow to the CPU, and continue on the loop. So starting from the CPU, run with callback is going to loop. It is going to call the tick on the boost, saying how many cycles it took. If program counter state equals program counter, blah blah blah. Okay, so this happens after the execution of the opcode. Here is the execution of the opcode. Okay. The boss should keep track of executed cycles and propagate tick call to the PPU, but because PPU clock is 3 times faster than CPU, it will multiply the value. So we have the new function. I think this is equal, except it now has a cycles variable. And the took function is adding the number of cycles and is calling tick on the PPU during 3 cycles. Sorry, the cycles times 3. Okay, that works well for this. And the PPU would track cycles and calculate which scanline it should be drawing. So the NES PPU now has variables for the scanline and for the cycles. And it is going to increment cycles, and it will start counting on 341 and will... Okay, so if it is over 341, it is going to decrease it and will increase one scanline. Okay. So it should never take an stupid amount of cycles. So this cannot happen more than once. If scanline equals 241, it's going to generate the B blank. Hey! Making none it. Is that the right way? Making none it. Thank you for the follow. How are you? Oh. You got it. Great. So, where are you from? What is the origin of your nickname? I cannot imagine it being it from your actual name, but maybe it is. And I am just... I don't want to say idiot. So... Status set b blank status true. I don't know what set b blank status is going to do, but if it works, it works. I am from Oregon, USA. My name is Matt. It is a reference to an album. Okay. I am not sure what album it could be. I was never good as I was never good with how was it? With music in general. Yes, you are correct. I am working on an NES emulator using Godot. So I am following this tutorial that is written for Rust. But I am translating this to GdScript. How was my command? Like this? Maybe not. Like this? Okay, forget it, I will just copy it. Ba-ba-bam. Where is the... Okay. I forgot my own command. Yeah, so it has its challenges because GdScript is not thought for integers of different sizes and signed and unsigned. They are all signed 64 integers. So I have to do some trickery to have the math work right. But I am having fun. So when the skyline is over 262, it is going to set the skyline to 0 again and reset the blank status. So this is basically setting and unsetting the blank flag, if I am not wrong. And why return true? Why does it return a boolean? This is not making any use of the boolean. So it only returns true if the blank is cleared. Okay. So blank happens from 241 to 262. It's the time that the CPU can update the background and sprites. Okay, that is useful information that we need to fix up in our minds. Some crucial details are still missing. Some of the CPU operations take variable clock time depending on the execution flow. For example, conditional branch operations like branch no equal take an additional CPU cycle if the comparison is successful, and yet another CPU cycle if the jump would result in program counter to be in another memory page. The memory page size 256 bytes. For example, the range belongs to page 0. Aha, okay. It is a node to compare the upper byte of the address to see if they are on the same page. I leave it up to the reader to figure out how to codify additional ticks that may or may not happen. Okay, that is not fun. So I think so far our dependency graph looks like in one direction. We have the CPU, the bus, the program ROM, the CPU RAM, and the PPU with the virtual RAM and CHR ROM. The problem is that we want to deliver signals from PPU to CPU, and Rust doesn't really allow have dependency cycles easily, but Godot does. I can choose the meta signal and be happy. The one way to overcome this is to replace the push model with pull. The CPU can ask if there are interrupts ready at the beginning of the interpret cycle. So before the loop, it is going to say let some NMI, and some I think it is the class used for optional, poll NMI status, and if it happens, it makes the interrupt in the CPU. The final piece is to implement the interrupt behavior. Upon receiving an interrupt signal, the CPU finishes execution of the current instruction, stores program counter and status on the stack, disables interrupt by setting the disable interrupt flag in the status register P, loads the address of interrupt handler routine from 0x0016 for the NMI, and sets program counter register pointing to that address. Okay, that looks straightforward. The interrupt handler would have to call RTI operation at the end to finish interrupt attendance. That would restore status flag and program counter position from the stack, effectively going back to the execution flow where it was left off. In addition to scanline position, PPU would immediately trigger NMI if both those conditions are met. PPU is B blank state and generate NMI bit in the control register is updated from 0 to 1. Aha! So if write to control, so if the status flag is changed from 0 to 1 and the scanline in certain range, okay, it has an is in B blank. This is more complicated than what we need, honestly. In our CPU implementation, we have implemented opcode 00 as a return from the CPU fetch the code executed cycle, but in reality it should trigger break interrupt. So this is a so-called software interrupt that a game code can trigger automatically in response to events. NetStep Wiki provides all necessary details about CPU interrupt. Okay? So we have read it, now it's time to get it coding. So according to this, the first step would be to have a ticking function in our main loop in the CPU. So the cycles are not tracked in the CPU according to this, they are tracked in the memory. So where is our run function? Okay, it is on the 6502. And where is the loop about to execute instruction? Okay, here is run. While it's running, it's going to execute the instruction and it is going to increase the program counter, blah blah blah. It is going to call the execution, and this is where the cycles are incremented. So we can say memory dot CPU cycles plus equal opcode cycles. Why is opcode not typed? Yes, it is cycles indeed. So now we can go to the, oh, that is probably why. We can go to the memory. Preferably the NES memory. Or we could have it in here. Our CPU cycles of type integer equals to 0 and has a setter set CPU cycles. So we have a function for this. Set CPU cycles with a new number. And this is all this do is setting the value. But in the NES memory, we can make an override of this function, like right here. So we call super first, and then we can call tick on the PPU. P cycles times 3. Why is super not working here? Oh, it is just this dump. Look, here it is. For some reason, this is not very smart. Let's reload the project and see if that helps. Okay, NES memory, and now it doesn't complain anymore. Awesome. So we can now have our tick function in the PPU. And the PPU is going to have bar cycles type integer equal to 0 and bar scanline of type integer equals to 0. So now cycles is going to increase by p cycles. So question, should I name that function tick instead of set cycles? Decisions. So it is probably better to have a normalized terminology. So the memory can tick. And the tick function in the memory, this is now tick, is going to increase. Plus equal, this was an idiot mistake. So this is meant to be virtual. Oops. So the NES memory is going to be called tick now, and it's going to call tick on the PPU. Yes, this is fine, but not parse global blah blah blah. And this is because this should not have this character in here. So now the memory is increasing CPU cycles, and this one does no longer have a should I make it internal? Yeah, I can make it internal. So cycles is also going to be internal, and skyline as well. Okay, perfect. So let's see how does it continue. If cycles is bigger than this magic value, cycles is going to decrease that same magic value. And scanline is going to increase. If scanline equals 241, which is the next scanline after the height of the resolution of the game, it is going to enter into P blank. So in here it is called control mask generate NMI equals true. It is the flag. Set P blank status. It is set into true. And if the skyline is bigger or equal to 262, it is resetting skyline and resetting the P blank status. I don't know why it returns a boolean, but let's do it the same way for now, because we are not very smart. So where was I? Tick. Here it is. What else was it? Oh, only that. Just oh, it is checking the it is checking the B blank status. Okay. So if control value equals true, it is going to the register status and set in B blank value equals true. Is this correct? And push warning to do should trigger NMI interrupt. Perfect. If scanline equals, and the magic number was 262, it is going to reset the scanline. It is going to reset the inv blank. And this one returns true. So this was meant to return a boolean. And if nothing of this happens, it simply returns false. So this is the tick function. We yet don't know what to do with it. So for the NMI interrupt, we can just use the signal NMI interrupt. What is the terminology used? Triggered. So now we can just emit the signal. And no longer need this to do. So now the NES CPU that has an NES memory okay, it is not specified in here. Okay. So what would be the best place to hook to that event? NES memory, what does it know of? It has the ROM, it has the PPU. It does not have a sense of its own CPU. What is this? Okay. Is there a soft reload scripts? Search, go to the book. Okay, nothing that is useful. I will ignore this for now. And we are going to have a copy of the signal of the PPU. Why did my music stop? There we go. So we have the NMI interrupt triggered. And we can have PPU NMI interrupt triggered. And we have set PPU. So if PPU not equal to no and PPU NMI interrupt triggered is connected to trigger PPU NMI interrupt. Let's create this. Function, trigger the function. PPU NMI interrupt triggered emit. Perfect. So if the old PPU is not new and is connected, we are going to disconnect it. And we set the new PPU and connect it. Yes. Yes. Perfect. So this is just a re-emission of the interrupt. So now we need a place where the NES CPU is connected to the memory. So we could use reset. Do we have a set memory function? Let's go back to here. Cannot find property cycles on type int. Oh, and that is because we should use the instruction cycles. That's why it was not auto-completing before. Okay. We can make the rule that our callbacks returns an integer with the number of extra cycles that it took. I don't want to give us an hard to understand name. Jump page is not the only reason, but for now let's do that. Did jump page and make it a boolean. So we have cycles, and if did jump page cycles plus equal 1. Is this correct? It only can jump 1. Let's take a look too. Oh, okay, I no longer have the documentation of the instructions here. So let's find it again. No, this is not it. It's maybe here. Yes. So it is always +1. So branch could take 2 more. Okay. So it can be more than 1. So let's name this extra cycles and let's make it a variant instead. If type of extra cycles equals type int, then we are going to increment by extra cycles. Perfect. So we can just return any value. And we can return it only in the callbacks that has a meaningful extra cycles. So we can fix that later using the unit tests. Let's hide this. And now we need a way to define how the memory is created. Do we want to initialize the memory and constructor? Oh, actually it is initialized, so that is perfect. So memory.ppu NMI interrupt triggered connect on PPU NMI interrupt triggered, and we can make this function. Function on NMI interrupt triggered. So the 6502 is using an NES memory. I don't quite like that. Should be using a normal memory. So I think I am going to use a normal memory here. No? It needs a size. Whatever. And we can take this and put it in the NES CPU. So the NES CPU is going to call super, and immediately after we can override that memory for an NES memory. And connect to the real function that we gave. Did we remove this function? No, we didn't. Okay. Really, I did not implement that? Okay. there is not much in the NES, so I will just put it after reset. So 1 or 2 spaces. What was I using in this project? Apparently 1 space. I get confused because I use different coding styles on different places. So this one should not have to. Oops. I can probably find in files. No, I cannot. It doesn't search unless I can escape it. No, it doesn't. And it doesn't have a reg. Anyway. And this one also doesn't accept new line. Well, that is not very useful. Have you made an emulator before? No, this is the first time. The little experience I have with retro consoles is because I once learned a little of assembly for Game Boy, but not much. The further I could make was a hello world with an horizontal scrolling of any text that I decided to print. Of course, hard-coded. So, okay, perfect. So now in the NES CPU I can attend to my interrupt. So what should I make? So I have a function of what should happen with the interrupt. What? Oh, right, I am in the wrong page. Back to here. So here is then my interrupt. Let's copy for now and start translating it after. What the hell? Okay. So stack push U16 program counter. So do we have a function like that? Yes, it's not an unsigned. That is the only difference. So it is taking a copy of the flag. How is the status flag called? Choose flags. Okay. Old flag is going to be flags dot value. What? Okay. So it is making a copy, changing some bit, and pushing the value. So I can theoretically make a duplicate. Does duplicate work with ref counted? Duplicate. No, only resource has duplicate. Okay. So bar auxiliar flag of type what was it? Now I forgot the name. NES register flags. And what was the arguments? Just the name. Auxiliar flag dot value equals flags dot value. So now I can use the auxiliar flags and set the break and break two. Was it break? Oh, it's B and B2. Okay. I don't like that it doesn't update. Oh, it did. I was just being stupid. So B2 dot value equals true. So now I can out flag dot value. And the status is exactly the flags. Flags, and which one is interrupt disable? Interrupt disabled, it's I, right? I suppose. Okay, so this is value. Stack push 8. Really? It ticks? And program counter is going to be equal to memory signet 6. What? I have to believe. Yes, interrupt disable is A. So I am going to copy this and put it in this class. I am going to replace this for this symbol. And now we have a better description of what is what. Perfect. So detailed interrupt behavior, delayed IRQ response, branch instructions and interrupt hijacking, IRQ and MMI tick by tick execution. And let's take a look. NMI interrupt is connected to an edge detector. This edge detector polls the status of the NMI line during what is the sigma 2? Okay, so it is a pin in the CPU of each CPU cycle. In example, during the second half of each cycle, and rises an internal signal if the input goes from being high during one cycle to being low during the next. The internal signal goes high during sigma 1 on the cycle that follows 1, where the edge is detected, and stays high until the NMI has been handled. The IRQ input is connected to a high-level detector. I don't know what is IRQ. I think it was mentioned. IRQ. Search IRQ. Nope. At least it's not mentioned in this code. If a low level is detected on the IRQ input during sigma 2 of a cycle, I suppose it is the second half and the first half. An internal signal is raised during signal 1 of the following cycle, remaining high for that cycle only. Or put in another way, remaining high as long as the IRQ input is low during the preceding cycle's second half. Ugh. The output from the edge detector and the level detector are polled at certain points to detect pending interrupts. For most interruptions, this polling happens during the final cycle of the instructions, before the opcode fetch for the next instruction. If the polling operation detects that an interrupt has been asserted, the next instruction executed is the interrupt sequence. Many references will claim that interrupts are polled during the last cycle of an interruption. Interrupts are polled during the last cycle of an interruption. But this is true only when talking about the output of the edge and level detectors. Whether that is a hardware implementation detail, I suppose. If both NMI and IRQ are pending at the end of an instruction, the NMI will be handled and the pending status of the IRQ forgotten, though it is likely to be detected again during later polling. The interrupt sequences themselves do not perform interrupt polling, meaning at least one instruction from the interrupt handler will execute before another interrupt is serviced. So I basically don't know what IRQ interrupt is about. What is IRQ interrupt? No, it's just interrupt request. So we yet don't know, basically. Branch instructions and interrupt. The branch instructions have more subtle interrupt polling behavior. Interrupts are always polled before the second CPU cycle. The operand fetch, but not before the third CPU cycle on a taken branch. Additionally, for taken branches that cross a page boundary, interrupts are polled before the PCH fix-up cycle. The one for a tick-by-tick breakdown of the branch instruction. Interrupt hijacking. Normally the NMI vector is at FFFA, the reset vector at FFFC, and the IRQ and break vector at FFFE. I see. This means that when servicing an IRQ, the 6502 will push the program counter and P, and then read the new program counter from FFFE and FFFF as in jump. But MOS 6502, by extension the 2A03 and 2A07, has a quirk that can cause an interrupt to use wrong vector if two different interrupts occur very close to one another. But I am not that worried about it unless it is very likely. For example, if NMI is asserted during the first 4 ticks of a break instruction, the break instruction will execute normally at first. PC increments will occur and the status word will be pushed with the P flag set. So the thing is, because our emulator does not have a sense of a real hardware, we only count the cycles when the instruction has finished. So these cases are not going to happen, hopefully. IRQ and MMI tick-by-tick execution. For exposition, to emphasize similarity with break, here is a tick-by-tick breakdown of IRQ and MMI divided from Visual 6502. A reset also goes through the same sequence but suppresses writes, decrementing the stack pointer twice without modifying memory. This is why the I flag is always set on the reset. So, what is this? I suppose this is the cycle. Read, fetch code and discard it. The break is forced into the opcode register instead. Read next instruction byte, actually the same as above, since PC increment is suppressed, also discarded. Push PCH on the stack, decrement S. Okay. Push PCL on stack and decrement S. At this point, the signal status determines which interrupt vector is used. Push P on the stack with P flag clear. Decrement S. So I don't know why of this address, but I don't mind. This is the accumulator. Fetch PCL A equals FFFE for IRQ and A for NMI. And is this what we have done here? Yes, we have set FFFI for the NMI. So we can make another function. Let's ask Google what is NMI interrupt. I hate acronyms. Non-maskable interrupt. In computing is a hardware interrupt that standard interrupt masking technique in the system cannot ignore. So I suppose we should forget about the part of the PPU. We can forget of the PPU, probably. Should say NMI and another one for the IRQ. On IRQ interrupt triggered. Okay. And now this one is going to push the program counter flags I value. Is this exactly the same except for this? So push P on the stack with P clear. Fetch PCA accumulator equals, is it accumulator, not program counter? E for IRQ and A for NMI. So it is E for IRQ. Set the I flag. Yeah, that is happening here. So this is the exact tick by tick execution. So this is program counter. However, I am not understanding why is it accumulator. So first it is reading. Address, read, write, description. So it pushes PCH on the stack. Let's see what is PCH. Nothing. PCA. Oh, I see. It's program counter high and low. This is fine. This is just pushing the program counter. Like here. This is what is doing those lines. So now it pushes the stack. Pushes P to the stack with the V flag clear. So it takes the stack, the P flag, clears the B flag, and pushes it to the stack. Okay, perfect. Now I understand. And now fetches program counter low and program counter high. It is fetched from the stack. No, wait. It's actually fetched. What? I understand. So FFA and FFP are the low and high. And FFE and FFF are for the low and high in the case of IRQ. So it's an automatic stuff of these. So the only difference from NMI interrupt and IRQ interrupt is this memory address. So I can make this a variable interrupt address. Interrupt jump address. I could make an assertion that only certain values are allowed. And use this value and don't have the function duplicated necessarily. This should be in parentheses. And this is just uninterrupt triggered. We go back to the start and we call this uninterrupt triggered and pass a different address to each one of them. So the NMI uses FFFA and the IRQ uses FFFE. Perfect. Perfect. So now it's doing what it is expected to be doing. So let's take a look to how the break looks like. So it fetches the opcode and increments the program counter, reads the next instruction byte and throw it away, increment the program counter, pushes high and low, decrementing the stack. At this point, the signal status determines which interrupt vector is used. Pushes P on the stack with the P flag set. Okay. Fetches program counter low and program counter high. So we would need an extra argument for the B flag. If we use break as well. So, and apparently the break takes to this. So what is exactly the idea? Is break the same as IRQ? This is not very clear to me, but it seems to be exactly the same. This one says A and A is FFFE. Do we have PRK? Okay, we are overriding NES break. Yeah, this should be renamed. CPU 60. Wait. CPU 6502 break. And this is doing basically the same. Okay, so now we can make an NES break. And let's override it in here. NES break. Function NES break. The NES break is basically calling this with the address FFFE and true. P break flag boolean. So we use P break flag this. And it should be false for the other two. Okay, perfect. And this is no longer needed. Perfect. Tick on base nil. Oh, the PPU is not set? Why is that? NES view. CPU equals match case and wall words. Okay. Let's remove wall words. It was never set. That is strange. It was working before. Hmm. Do I choose create a new one on init? Wait a second. Okay, it wants the ROM. CHROM is null by default. Oh, it's an empty array. That's fine. So we can pass null. Or even pass ROM. So, where is my music? So, let's run this and see what happens now. So it doesn't have a function memread. Oh, it's probably just 16, not unsigned 16. And its program counter value. Okay, it is attempting to write on the cartridge. How did this go? Okay, we have gone beyond break now. And that is why we stop it, basically. Okay, awesome. So for now, let's say running equals to false, at least for now. Okay, and now it's not taking an error. Perfect. So I think we are safe with the 3 types of interrupts that can have the NMI, the IRQ, and the break instruction from the code. The break instruction is kind of manual, I think. And I don't really know what it is about. Like, what is the right way to use it? But I think we are fine for now. So let's make a commit with this. Let's see. So yes, we added CPU cycles to memory. We changed the memory of the 6502. We changed the name of the break code in the 6502. Got extra cycles from the instruction and tick the memory. Added some comments to the register flag. And the NES CPU has a NES memory now and connects to the interrupt, and has a redefinition of break. We have a handle for the interrupt that takes the new program counter address and the break flag value. Is that the name of the flag? Is it break? Yes, it's break. Okay, perfect. A new signal in the NES memory. And created a PPU by default. Added the function to tick. Added the forwarding of the interrupt. And the PPU has cycles and skyline and the interrupt. And safety check to see if we can initialize without a ROM. The tick function and a lot of new line removals. We added an update function that right now is unused, and we never made use of this code for observing memory. So git commit, and what we did with this was implement NMI interrupts coming from PPU. So now that we have cycles tracking, we can start having that extra cycles coming from different instructions. And to do that, I think what I want is using the unit test. This part of the code that I was ignoring, I want to start populating it. So So let's go to the unit test. I will probably revert it because we are not looking at this memory or anything. I don't know, it is nice to have the template. Whatever. So now the output of the trace it dumps registers. The dump of the registers ends with the space or not. Oh, it has the space, SP. Okay, so the next is dump PPU. Out plus equal dump PPU, and out plus equals dump cycles, or dump CPU maybe, dump CPU cycles. So this is the two functions I want to have now. So after dump registers, let's make those new functions. And they should return a string. So let's copy this very quick. It's going to return out right away. Perfect. So the PPU is going to be out plus equal doesn't even need a new line in here, so we can just format it. PPU equals, let me see how is this. Okay, it uses spaces. PPU digit space, and this is 3 with a space. How is the format integer Python? Not interested. The old and new. Yes, yes. $110s. Okay, so I can say 0D, sorry, 3D without this. and without the 0 it should put spaces. Is this correct? So I can now use memory PPU bar mem is an NES memory equals memory as NES memory. So now I can use mem. Okay. Now I have access. Get register scroll dot. Do I need a dot value? That's right. Oh, it's a write only. Write to scroll, blah blah blah. Okay, I have scroll offset. This is what I want. Perfect. .x mem PPU scroll offset .y. This is what I wanted. Okay. So now this one is cycle. Oh, it was not equal, it was colon. Does it has a space? No, it doesn't. Does it nestlog? Is it? No, it is also not aligned to the right. So it's cyc and then an integer, and the integer is memory CPU cycles. Wait a second. Okay, I will just make it public and forget it. So what happens now? What? Get index minus 10. So now trace is not going to use the trim. Wait a second. Let's make a breakpoint here and let's see how it starts. Log line and trace line. Aha! So it is making the trace the log starts with PPU on scroll 21. Why is that? Is it the default? But also cycle is 7 and not 0. So is it pre-pending the tick before the trace? Oh, it's probably that I am overriding the run. I don't think so. See, run comes from 6502. So about to execute instruction is going to run. And this is the very first line. Let's see the NES log. The very first line. So maybe, oh, this is the scan line. And this is the frame. I see. And it never clears, right? Okay. Let's do that. I thought it was scrolling, but it was not. Anyway, it starts in scanline 21. That is strange. Oh wait, no, it's the cycle. 7 times 21. That's interesting. So this is the cycle and this is the scan line. Okay, that's much better. I made a wrong assumption of what I was supposed to be testing. So it's actually better. Do I make it public? Okay. So this is cycles now. So we are still wrong because this part happens after the execution, not before. And that is strange. How do I solve this? So we have a trace, about to execute instruction. did execute instruction. Bar retrace string, and we can make retrace equals trace start and emit with retrace plus trace end. This is trace start and this is trace end. Copy this here, copy this here. Okay. What is it? Trace end not found. Oh, end. So we can call did execute instruction after the tick. Not the best, but should work. Okay, that has gone bad. Clear, and let's have a little print and then stop. So, what is gone wrong? So first, we got a very bad amount of cycles. Why only 3 cycles for jump? So the instruction is for C. Let's see in the do I have instructions reference? file format, hardware, installations, notes, external link. Okay, let's find it in here. Here it is. Force D. It says it takes 3 cycles. So what is going on? Is this false? Wait, this is not absolute. No, it is absolute. Do we have another reference? What is it? There was a list of many links. This one. Okay, perfect. Force D. It takes 3 cycles. Indeed. So what I am doing wrong? Now I am confused and concerned. When did it become very bad? Okay. So there was an overflow. And then everything becomes very shitty. But this is matching until this point. So the overflow is breaking some assumption. Okay. So we have a problem. Is this something we cannot relay? Seven plus 3 is 10. So this is indeed a starting value, I presume. So maybe I have to come to the unit test, and in the init CPU.memory.CPU cycles equals 7. CPU.memory.ppu.cycles equals 21. And now we don't need anymore the after. Did Execute instruction, no longer needed. No longer needed. Damn. And in the NES CPU, not in here, in this one. It execute instruction, no longer needed. So now we don't need this. We don't need this. We don't need this. We don't need this. Don't need this. And don't need this. And I think this is famous last word. Okay. Do some prints and let's see what do we have. So the first mistake is happening at the no operation. But why is it not printing the previous line? So I did something wrong in the code that I changed it. What if I remove this? Okay, so if absolute of age is smaller than trace history.size, then you print it. House. Okay. Okay. Wait a second. Why is this printing only one? It's because they match perfectly? Oh, it matches perfectly. That's awesome. So let's make this a 4 character line number. 4 is the longest, right? Yep, 4. Okay. House, and let's go to the start again. So now the first mismatch is happening on BCA and BCS. Wait, what? Oh, I see. So I need to have 4 and 4 also in here. Okay. Perfect. So let's see git add import. So yes, we rename it this. We rename it this. Added dump the PPU and cycles. Initialization of value. So those cycles, I am assuming they are needed for the reset process. So I could also memory tick 7. Anyway. Yes, this is correct. To avoid a mistake. And I want to rename dump PPU to dump PPU cycles. Git add p. Yes. Okay. Git commit unit test now compares CPU and PPU cycles. Git push origin. That was nice, actually. Okay, I think that's all for today. So, thank you very much for coming and see you on the next stream.